We consider a scalar field coupled to gravity. In particular, we consider the following action. We have an action which depends on the field phi and g mu nu, the metric tensor. We define this to be equal to 1/2 integral d2 omega x. Now this 2 omega is simply the dimension of our space, of our space-time. So in general we might have omega equal to 2. It means that we have d equal to 4 if we define 2 omega to be equal to d, which is the number of dimensions, as usual in special and general relativity. But for now, let's use this notation. Then here we have the square root of minus g, where g is the determinant of the metric tensor. And here we have g mu nu. We have the derivative, which I will denote like this, phi comma mu, which is the derivative of phi with respect to mu. So it's d phi dx mu. This symbol, this notation is also used for covariant derivatives. When we have a scalar, the covariant derivative of a scalar is simply the gradient of the scalar, so it is calculated like this with partial derivatives. But if we add a vector field a mu, if I use this notation, for example, where I put a comma and then nu, this means the covariant derivative calculated with the index nu, and here we have a mu, something like this. So the covariant derivative contains the partial derivatives and also the connection. Then here we have phi comma nu minus v of x phi squared. So in particular, v of x, you can think of that as a potential, and it plays the role of the effective mass of the field phi. The Greek indices run from 0 to 2 omega minus 1. And let me repeat it, if 2 omega is equal to 4, so if we are in 4 dimensions, this is equal to 3. So we have the usual 4 components, 0, 1, 2, 3, right? Now, we perform the so-called analytic continuation of this action here, and we want to go to Euclidean time. So we make the so-called weak rotation. Weak rotation, which is usually done in quantum field theory, to move from the signature plus minus 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 to the signature minus 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 minus, because we change from the zero component here, which is related to time, we can call it t. We go from t to it, so we put this imaginary unit, and therefore, if you recall, in special relativity we have something like this. We have dt squared minus dx squared minus dy squared, or if you want, dx1 squared, dx2 squared minus dx3 squared, something like this. And this is, of course, x0. But if we change t to it, then of course here we get a minus, because we get I squared, which is equal to minus 1. So the signature changes like this. And let me also mention the fact that this action here contains the interaction between the field and the gravitational field, so the field phi and the gravitational field related to the metric tensor g mu nu. And if we, for example, want to consider the dynamics of the gravitational field by itself, we have the Einstein-Hilbert action, so something like this, S Einstein-Hilbert, with some modifications if necessary to account for quantum corrections to the theory, whatever. But this accounts for the gravitational field itself, only for the gravitational field, whereas such an action is some kind of interaction. If we consider an overall action, we might have plus other terms, like this one, so S of phi g mu nu, and possibly other interactions with other fields if we have other fields. Now, as I said, I want to make a weak rotation, and the action changes with this signature. Let me also tell you that from this signature with all minus signs, we can go to a signature with all plus signs. And how can we do that? Well, we simply replace g mu nu with minus itself. So we might call this like the Euclidean metric, ge mu nu. So we define it with a minus with respect to the initial g mu nu. So by taking this into account, we can rewrite this in the following manner. In particular, if we factor out the I from it, so if we factor out I here, we get a factor of I over 2, then we have an integral d to omega x, and in this case the first component of the coordinate x is t, so we have t and then some vector x, some 2 omega minus 1 dimensional vector x, because we have factored out I. So either we put a factor of 1 over 2 and then we put the factor I here, or we factor out I and then our vector becomes like this, tx, just like before. Then we have the square root of ge, so this is the determinant of the Euclidean metric. We call this the Euclidean metric. And then we get a minus g mu nu e, and we can put the minus here, so we have g mu nu, actually here we have upper indices, and let me put the e here. We have phi comma mu, phi comma nu. Then here we get a plus because we have factored out a minus, so here we change the sign, v of x phi squared, like this. And at this point we can define the so-called Euclidean action. So remember where we started from here, and this is related also to the path integral formulation of quantum field theory. This action appears inside the argument of an exponential of the kind e to the I s. But since here we have factored out minus I, when we multiply it by I, it's as if we get e to the plus the action, and in this case we define this to be the Euclidean action. Now we need to be a little careful when we talk about the exponential of the action, because here we have a plus, but if we put a plus we get an exponential which explodes rather than decays. So if we start, for example, from e to the minus is, we will also get a minus here. Or another alternative is to make the change of variables in the weak rotation from t to minus it instead of plus it. So for the sake of convenience, let's leave things like this. So I will not change this sign either. But remember that when we consider the effective action, and in particular the path integral related to the effective action in Euclidean space, we would have something like e to the minus the action. So it's as if we can define this to be minus I, then we have an effective action which depends on the field phi and also g mu nu e. And remember that we have set t from t to it, so we have changed it like this, and we changed the metric g mu nu to g mu nu e, but I will not write it. And also let me tell you that in the following I will simply drop this index e, because it is just something that makes the notation more cumbersome. We have to remember simply that we use the Euclidean metric, and we can also simplify this minus I with this minus I here, so we get 1/2, and therefore here we don't have an equality anymore, but whatever. And this is the formula that we get. And let me also drop this limit. We have to remember that we have changed the t to the I, so we have made the so-called weak rotation. And now let me do one more step in particular, we can integrate this term by parts in the integral by assuming that the field phi decays quickly enough at infinity, which means that we can basically omit boundary terms because they go to zero. Therefore, we can rewrite the effective action in the following manner. This is equal to 1/2 integral d to omega x. Then we have minus phi square root of g. We have g mu nu. Then we have phi comma mu. And then we have comma nu of this expression, because we have integrated by parts this term here, so the derivative will only act on this term, and we have changed the sign due to integration by parts. Plus, then we have the square root of g, the potential times phi squared, and we can rewrite this more concisely by defining the following operator. In particular, we define, so here we put square root of g, then we have phi of x, and we define an operator which we call f hat acting on phi of x, where f hat is equal to minus this D'Alembert operator, which is some covariant D'Alembert operator. It is also known as a covariant Laplace operator. I will write its expression in a moment. And then we also have plus the potential. And the covariant D'Alembert operator acting on a field is given by 1 over the square root of g d mu square root g mu nu d nu phi. And if you replace this expression here and then you put that in here, you will get exactly this expression here. Now, it is convenient to write the action in this form because we can discuss it more in detail, and that's what we will do, in order to understand how we can deal with such an operator and what it tells us regarding this theory.